Okay, let's get started. All right, today's lecture is going to be our final lecture related to oscillators. We're going to look at crystal oscillators. And actually, a lot of what we talk about today applies more generally to any kind of high Q resonator, especially mechanical resonators that you might use to build an oscillator. So first of all, a crystal oscillator, what does the schematic look like? It looks something like this. And the reason it looks like this is that if you actually look at a real crystal resonator, it's usually a structure very similar to this. We have two plates, and in between we have a material such as quartz. In fact, quartz is the material of choice for building crystal resonators. Quartz is a piezoelectric material, which means that if you apply a voltage between these two terminals, you get a mechanical displacement. So you can induce a mechanical oscillation to occur inside of this material. I should have brought in some nice examples. I have some crystals that I could show you. Maybe next lecture I'll bring them in. Or if you come to my office, I can show you some of these crystals. They come in different shapes and packages. For instance, a canned crystal might look something like this. The equivalent circuit for it looks like this. You basically can model each resonant mode with a series LCR circuit. There is a physical capacitor, which is just basically this parallel plate capacitor. Let's call this C0. We can call this L1, C1, R1. And because it has multiple modes of resonance, basically the harmonics, you have to model those as well. So this might be L2, C2, R2, which is the first overtone, maybe another overtone, and in fact there are an infinite number of overtones. Usually we're concerned with the fundamental mode. These are the overtones. And this is actually a physical capacitor, as we talked about. Okay, so this is the equivalent circuit. Anytime you see something like this, you can put in an equivalent circuit like this. And if you know what you're doing, if you're only concerned with one particular mode, and you've taken precautions to suppress the other modes of the circuit, you can just use a simple series LCR with that capacitor to model it. Okay. Now, question?
Where's the C0 from again?
The C0 is just this CAN capacitance. You just have two terminals, right? This is a dielectric, and so it's basically a capacitor. If this were not a piezoelectric material, all these elements would go away. You just have a capacitor.
In parallel, not series.
Because it is in parallel, right? What you're doing is, forget about all this stuff, right? It's just a capacitor. And what happens in between is you induce waves that flow back and forth here. And in fact, there's a good reason why this model works. It actually goes back to some fundamental theory. From an electrical perspective, this is a two-port device, and it has some frequency-dependent impedance. It turns out that you can model any arbitrary impedance with an equivalent circuit that looks like this, where these catch the resonant modes of your circuit. Okay, so this is an equivalent circuit. Talk a little bit about the acoustic wave properties. The acoustic wave has a phase velocity v of about 3 times 10 to the 3 meters per second. This Sharpie isn't so sharp. Let's see if we can do a little bit better with green. So for instance, if the material had a thickness of 1 millimeter, then the delay time for a wave to travel, which is the first resonant frequency, is 1 millimeter divided by 3 times 10 to the 3 meters per second, or about 1/3 microsecond. Okay. And that corresponds to a resonant frequency, F naught, 1 over tau, or just velocity over thickness, of 3 megahertz. Okay, and this is the basically, so our equivalent circuit here, the first mode, L1C1, should resonate at 3 megahertz. Okay, so we know how to pick the product of L1C1. How do we pick the value of L? Anybody want to comment on that? I'm sorry? Well, what would that, something in terms of electrical parameters, what would it depend on?
Is it the lead length of the device? If it's leaded, like you showed there?
No, so don't confuse this equivalent circuit. This is an electric equivalent circuit for this, right? Right? Yeah, the Q of the circuit, right? So this is a resonant circuit. Product of LC tells us where it resonates. The value of L over R tells us what the quality factor is, right? Remember, this is a mechanical resonance. Now, this is the reason we use crystals, is their quality factor is extremely high. So about 3 million in vacuum and about 1 million in air, which means they have extremely good frequency stability. And if you think about our discussion last lecture where we discussed phase noise, we found that phase noise was directly proportional to Q squared, inversely proportional to Q squared. So obviously the way to design a very stable reference with a good spectral purity is, one brute force method is use the highest quality factor tank that you can. And you cannot build electrical resonators, purely electrical resonators, approaching 1 million quality factor. You have to in fact use mechanical resonators. Now, one of the problems with this technology, with the quartz technology, is a frequency limitation, because the highest frequency you can go depends on the thickness of the material. And commercially you can buy up to about 200 megahertz crystals, which corresponds to a thickness of only 15 microns. So if you go below that, the material is harder to design with good frequency stability and accuracy. MEMS resonators, though, have been demonstrated up to gigahertz frequencies with also very good quality factors. Okay?
Question.
Yes.
Is there a lower limit for the MEMS resonators?
That's a good question. I mean, I don't believe so, because you can get even kilohertz range crystals, let's say for a watch. Below kilohertz, they probably start to get physically just too big. Okay, so let's look at some typical crystal values. Let me just say one thing. Yeah, that's all I'll say there. Okay, so let's look at an example. Let's say you go buy a crystal resonator and you find the fundamental mode has the following equivalent circuit: C0, L1, C1, R1. C0, let's say, is 3 puff. Okay, that's a very nice value because it is a physical capacitor. It's something you would expect. But look at the value for L1. It's a quarter Henry. Okay, this tells you this is not a physical inductor. It's actually a modeling parameter which models a mechanical resonator. It's, you know, that's a huge inductor, right? C1 correspondingly is very small to give us a resonant frequency of 1.6 megahertz. And R1 is 50 ohms. So for this particular crystal, at resonance, at series resonance, the quality factor is 50,000. Okay? Now, because the quality factor is so high, if we look at the rate of change of phase for the circuit, it's extremely abrupt. So we know that a series LCR circuit at very low frequencies, it just looks like a capacitor, right? And so the phase shift would be minus 90 degrees. For really high frequencies, it looks like an inductor, so the phase shift would be 90 degrees. Exactly at resonance, the phase shift is 0 degrees. And we know that it'll change smoothly from minus 90 degrees to plus 90 as we cross resonance. Now what's interesting is if you look at what frequency offset do you need to go to shift by 45 degrees, you'll find that it's omega s over 2q, where qs is the series resonant frequency. And you can also show, and we've discussed this before, that for a simple second order system, the quality factor is really the rate of change of phase with respect to frequency at resonance. So it's this slope times the frequency of resonance divided by 2. So this slope determines how quickly this changes. And that means that this whole delta omega, so that means that a 90-degree phase shift corresponds to only shifting the frequency by omega s over q, right? Because this is 1/2 of that, and delta omega is twice that distance. Well, because the quality factor is so high, we can see that delta omega over omega s, which is 1 over quality factor, can be extremely small. So if our quality factor is, let's say, 50,000 in this particular example, that corresponds to 20 parts per million. So the nice thing is that if you build a circuit with this, a resonator with this, it's going to have extremely good phase accuracy regardless of any kind of excess phase that you may have in your feedback loop. So automatically it means you can be pretty sloppy in designing your circuits. It'll still resonate very close to where you think it should. All right. So how am I going to use this resonator? Okay. The question? Well, one important concept is that there are two modes. There's a series mode and there's also a parallel mode. Okay, so the series mode, if I think of this simple model for the circuit, the series mode would correspond to, let's say, resonance occurring through here. So omega s, we call the series resonant frequency, has a very small impedance. If this is very small, it looks like a short circuit, right? On the other hand, the parallel resonant mode is basically a frequency above omega s. If I go above omega s, that means that this starts to look inductive, this branch, and so I have an inductor in parallel with a capacitor, and it will also resonate at some mode. So in parallel resonance mode, there'll be a resonant current circulating here, and from my terminals I see very high impedance, or practically an open. Sort of. Okay. And in general, we can see that the parallel resonance mode is higher than the series resonant mode. Okay. That makes sense to everybody? This is an important concept that we'll come back to again and again when designing crystal resonators. If I were to plot the reactance of the circuit versus frequency, the plot may look something like this. This is omega s, this is omega p. At series resonance, the reactance is exactly 0. At parallel resonance, the reactance is infinite. And in between, there would be a curve that looks something like this. So I go from a capacitive circuit at low frequency, right? At low frequency, this branch looks like a capacitor. This is a capacitor. They're in parallel. I hit series resonance. The reactance goes to 0. And then I go to parallel resonance, where this basically just shoots up to infinity. So the key point is that in this region, the crystal looks like an inductor. Okay? That means that to build an oscillator, all I have to do is replace my inductor with a crystal. So here's a Pierce oscillator, C1, C2, and I have an inductor here. And I know that in a Pierce oscillator there's a resonant current I0 flowing here that generates a V in and a V out. And a Pierce oscillator V in therefore is approximately minus, because this current, let's say, is going in this direction, minus j omega C2 I0. V out, on the other hand, is plus 1 over j omega C1 I0. And so V in over V out, which is tells us the n factor in a Pierce oscillator, is minus C1 over C2. I could take this same circuit and just replace the inductor with a crystal. And again, a resonant circuit will flow in this path, and it will oscillate just as you expect. The difference, though, is that the quality factor now is much better than you could achieve with an inductor. Okay? So I might have an on-chip inductor with a quality factor of 5 or 10. Go off-chip, I can get a more expensive inductor. Maybe I have a quality factor of 30 or 40. I use a crystal, I get a quality factor of 1,000,000. Right? You can't beat that. That means that you have to be really careful that when you build a circuit, you don't DQ the crystal. Right? And that, in essence, dictates what topologies you would or would not use. So if you think about the other, this is basically the Pierce is a grounded emitter. Think about a grounded collector or grounded base, and you'll find that both configurations will actually load the crystal with the transistor impedance. So we pick the configuration that has the least loading effects on the crystal.
A question?
Yes.
So far we always have assumed that the Q of the inductor dictates the overall Q because it's much lower than the Q of the capacitors. But now, since we have such a high Q inductance, what about the Q of the capacitors?
That's an excellent point. Yeah, you have to, when you're talking about a Q of 1,000,000, you have to include all the loading effects that will occur. Capacitors generally have good quality factors, much better than inductors, but it depends on how you lay them out. So you have to be very careful that you lay them out in such a way that they have the minimum lead. Basically, the resistance of the leads doesn't DQ the capacitors. You also have to make sure that you use good quality materials for your dielectric, because the dielectric loss can lead to a reduction in quality factor. So the neat thing about this circuit is that the crystal can take on any appropriate value L effective. Say this is L effective, this is L effective, to resonate. So it's almost, you get it for free. You stick this crystal in there, it figures out what value inductance it needs to resonate with these guys. Loop gain's bigger than 1, it starts oscillating. Right? It seems too good. Right? Now this would not be useful because at this point we don't know what frequency it's going to resonate at. Right? It's going to be some frequency between omega s and omega p. But as I'll show you guys in a couple of slides, those frequencies are extremely close together. The series resonance and parallel resonance are almost right on top of each other. So in a very small, narrow range of frequencies, I can make this circuit oscillate. And so it's a very predictable frequency of oscillation.
So, but then I can use the capacitors to tune it, right? A bit.
A bit.
A bit.
Yeah,
So basically, I need to stay in the inductive part, right, of the
that's
slide you
right.
showed before.
Yeah.
Is there any difference, or is it?
You don't have to use the inductive part. You can actually, you can build resonators that work in other regions too.
Okay.
But we'll look at that later in the lecture. Yeah, the reason that it's hard to pull the frequency is exactly related to why omega S and omega P are so close together, right? And we'll talk about that a little bit more. A couple slides back, a couple lectures back, we talked about clock drivers. Almost all circuits need timing reference, right? So if you have a microprocessor or high-speed logic circuit, you need a good clock. Often you'll come off chip to connect to a crystal, let's say like this, and this is your clock reference. And the nice thing about this Pierce oscillator is, let's say in a MOS technology, you might realize it as follows. This is your current source, and you might have a feedback resistance to bias up your circuit. You have your C1 and C2, and then basically you have pins that come off chip where you can connect your crystal. Well, the nice thing about this circuit, well, let me just draw just to make sure you guys see that this is nothing but a Pierce. Okay, this is the same Pierce that we've looked at before. I'm just realizing this resistor with a MOSFET and this current source with this PMOS device. So this might be in a low-cost process. The beauty of this circuit is that if I don't, I can either put in a crystal, and this will be the clock for the system. If I happen to already have a clock, I can just drive that clock on the input, and this circuit acts like a clock driver, because if I don't, basically the equivalent circuit without the biasing, without the crystal, is just C1, C2. You've already sized this transistor up to be a pretty hefty device, and so it can act as a clock driver. So it's a nice, cute little way of achieving both. Okay? Questions? Yes?
What is the MOSFET in feedback for? What does the resistance do?
That's just to bias it up. Yeah. Yeah, because it's a self-bias configuration, so it's a diode-connected MOSFET device. All right, so how is the temperature stability of these crystals? Well, if you look at the thickness, the material, it's a mechanical piece of material, and it changes thickness with temperature. It changes about 14 parts per million per degree C. So this is the thickness. So if you just built a normal crystal oscillator, you would get, effectively, this would translate into your temperature coefficient. But it turns out that the phase velocity also has a temperature coefficient. So if you cut the crystal in a certain crystal orientation, you can cancel out the temperature coefficient of the phase velocity with the temperature coefficient of the thickness, so that overall, it's not a perfect cancellation, but your frequency stability becomes about 0.6 parts per million per degree C. That's pretty good. To give you an idea of what that translates into, 1 second per month translates to 0.4 ppm. So if you built a watch with one of these crystals, it would deviate about a second a month. Not too bad, not too bad. In terms of frequency stability, that's about 0.4 hertz in a megahertz. Give you another way of looking at that stability. It's interesting to translate this 0.4 ppm stability into, if into just a change in thickness. So if I have a 1 millimeter thick material, delta T would be 0.4 parts per million times T naught, which is 1 millimeter, and that's, so T naught is 10 to the minus 3, that's 10 to the minus 9, so it's 4 times 10 to the 10 minus 10, or just 4 angstroms. Corresponds to a change in about 2 atoms. So that's a pretty amazing amount of stability. Just to take a couple atoms away from the thickness, and your frequency would change more than 0.4 parts per million. If you look at the frequency stability delta F over Fs over, let's say, a standard range, minus 55 degrees C to 125 degrees C, you'll find that people have engineered things, obviously, to work at room temperature. So this curve goes through a nice zero right around room temperature. And at the peaks, it's about 15 parts per million. And the average temperature coefficient over this range is about 0.3 parts per million per degree C. Okay. So what if you need to do better than this? What if, 1 second per month is too much? Well, one thing you can do is you can put your crystal in an oven. Just hold the temperature constant. That's an oven compensated crystal oscillator. And your oven would take about 1 inch cube, and this technique, something maybe in the military that you might use if you have all the money in the world and you're only building 10 parts, can get you down to 0.01 parts per million per degree C. Okay, I won't calculate how many fractions of an atom that is. More common is actually temperature compensated crystal oscillator. And this goes back to what Michael Mark pointed out, is we can use an external capacitor to basically tune the resonance frequency. So here I have a control voltage, say this is a varactor, and I'm going to pull the frequency of this circuit. So how do you come up with this voltage? Let's write a few words down. We're going to use a varactor in series, let's say, with a crystal, and vary the varactor voltage to vary the capacitance with temperature. And so this actually, the voltage here might be digital or analog. More likely it's probably a lookup table. So you have a temperature detector on chip. It detects a local temperature, looks up in a table and says, okay, I need a voltage of 0.7 volts for this temperature to compensate. And at the end of the day, you can get pretty good compensation on the order of 0.05 parts per million per degree C. Incidentally, the same kind of techniques can be used with MEMS resonators. When people initially designed MEMS resonators, one of the concerns was that you cannot get the same temperature stability that you can get with a crystal resonator. But using the same kinds of techniques, you can actually, digital comes for free, so the logic to implement this might just be a tiny little area on your chip, and so you can compensate for that, for those variations. All right, so let's look at a little bit more detail what the equivalent circuit looks like at different frequency ranges. So clearly below omega s, the series resonance frequency, our crystal just looks like a capacitor. So what's the value of the capacitance? Well, all we do is set the value of capacitance equal to the equivalent circuit value. Let's assume the fundamental mode is all we are concerned with here. And we can do that because at the first resonance, let's say the next mode is at, let's say, 3 times the frequency. Those basically reactances have negligible loading. So we have our crystal, and we're forgetting about the Rx for now. Let's just simplify it. So these are in series, and then they're in parallel with Cx. Well, because I'm below resonance, I can factor this term out, and I get 1 minus omega squared Lx Cx. This term is positive, so this looks like 2 capacitors in parallel, so that C effective is C naught plus Cx divided by 1 minus omega over omega s squared. Omega s is the self-resonant frequency, series resonant frequency. So the effective value of capacitance looks something like this. At low frequencies, it's C naught plus Cx. And then it shoots off to infinity as we get closer to the series resonant frequency. Okay. Any questions? Crystal clear. All right. So how about in this frequency range that we so care about? Well, in this frequency range, clearly it's an inductor. And the effective value of inductance, we calculate it in the same way. We have an external physical capacitor in parallel with a series circuit, series resonant circuit. So now I factor out j omega Lx to keep this term positive. And so you can now easily see that the value of effective inductance is this inductance, which is reduced by the effect of this capacitance. So if this is L effective, this is omega, this curve is only valid in this range from omega s to omega p, and it will shoot up to infinity like this. So the crystal displays L effective from 0 to infinity henries in a finite frequency range. And that justifies that for any C, the crystal will resonate somewhere in range omega s, omega p. Okay. Now, question.
Yeah. So what about the? I mean, I have different values of L depending on which frequency I resonate. But what about the Q of the resonant circuit then on across along the whole?
Yeah. Well, what I'll show you entirely is this is an extremely small range of frequencies, so the quality factor changes very little in this range. Okay. So, using this equation, basically plug in omega p into this equation. So if I plug in omega p L effective has to equal to 1 over j omega p C naught j omega p Lx 1 minus omega s omega p squared. And I'm going to save us some time. You do a few lines of algebra, you can solve for the ratio of omega p to omega s, which is 1 plus Cx C naught square root. Okay? And again, let's look at an example to see how numerically what that looks like. Cx is 0.04 picofarads, C naught is 4 picofarads, so much bigger than Cx. And numerically that corresponds to a ratio of 1.005. So extremely small. So these frequencies are indeed very close together. So if you buy a crystal and it says that it'll resonate at 1 megahertz, they're actually on the can, it'll tell you what external capacitance you should connect for it to resonate at that 1 megahertz. So the crystal manufacturer already is assuming that you're going to put some C in shunt. And so when you design your circuits, you should make sure that your capacitance is equal to that, to what they're telling you to put. And usually the value of capacitance is pretty reasonable. It's something that you can easily achieve. It's not femtofarads or attofarads. It's actually on the order of hundreds of femtofarads to picofarads. And you put that capacitance in parallel, and you will hit that resonance frequency dead on. Okay? Questions? This is your favorite topic,
Yeah,
it seems. You're a watch maker in a previous life?
Maybe, yeah. Maybe I'm becoming one. No, but just to go back, so with the capacitors I attach, basically,
Yeah.
I can choose any frequency between omega B and omega S.
That's right.
Without any difference in, say, Q or anything with
Yeah,
the oscillator.
Yeah, because this is such a small range, the quality factor is going to change less than 1%, right? All right. So let's actually look at the yeah, so one way to choose it is to actually look at the manufacturer's data sheet, and they tell you if you want to hit this frequency, which is some very well-known reference frequency, you should choose an external capacitance of, let's say, 1 picofarad. So you would design a circuit that loads it with 1 picofarad, and you'll hit that reference frequency. All right, so let's look at the losses, which are actually really important because they ultimately will DQ our circuit. So let's go back to this Pierce oscillator. Again, we're looking at the Pierce because it's a popular topology, but by no means do you have to design a oscillator that looks like this. The equivalent circuit is Rx with JXC here. Again, C1, C2, this is our transistor. And what we'd like to calculate is the effective impedance ZL prime. Because I need to find my loop gain, so I need to multiply GM by ZL prime to design my crystal oscillator. So X1 is just the reactance of this capacitor. It's minus 1 over omega C1. X2 is likewise minus 1 over omega C2. And the reactance JXC corresponds to the reactance of this crystal, which is just J omega L effective. Okay? So ZL prime is this, and to first order, it's this impedance in parallel with impedance if we neglect the effects of R pi. So that means that it's the product of JXC1 times this impedance, which is Rx plus JXC plus JX2, which is this guy, divided by the sum, Rx plus JXC plus JX1 plus JX2. Right? Well, this denominator term is quite nice because in resonance, remember, where's the resonant current flowing? Resonant current flows in this loop. That means that this element, JXC, is in resonance with a series combination of C1, C2. So all of this is identically equal to 0 at resonance. Okay. Also, if I look at the numerator, that means that JXC plus JX2 is equal to minus JX1. So I can substitute minus JX1 in the numerator. So ZL prime is JX1 Rx minus JX1 divided by Rx, or multiplying this out, I get X1 plus JRX ratio of X1 to Rs. Now we're going to make a high Q assumption, in fact a very high Q assumption. And the assumption is that because this is a very high Q circuit, this reactance is much bigger than Rx, which means that since this element is in resonance with a series combination of these elements, the series combination of these elements is also much bigger than Rx. And if these are on the same order of magnitude, that means X1 is much bigger than Rx. This is X1. So that means that I can drop this term and calculate approximately X1 squared over Rx. So this is the crystal loss reflected to the output of the oscillator. Okay. Now it's interesting to look at what this means about the overtones. As we go to higher frequencies, so if I go look at the third overtone, that means X1 is smaller, right? And that means that the effective resistance is much smaller. So the shunt loss is actually, so if I translate this to the output for higher overtones, I actually get less loading at the overtones. So if I compare the loop gain at an overtone frequency, because this term is smaller, in fact, I should correct myself, I get more loading at the overtones because this is a lower impedance, because it's in shunt. So let me write that down. So X1 gets smaller for higher omega. Therefore, the shunt loss reflected gets smaller. That means I have more loading at the overtones. That means the loop gain is therefore lower at overtones compared to the fundamental in the Pierce oscillator. So that means we can easily design for loop gain less than 1 at overtones. And this is important because if the loop gain is bigger than 1 at an overtone frequency, you might actually end up oscillating at an overtone, or you might end up oscillating at 2 frequencies simultaneously. So instead of producing a spectrally pure output, you produce 2 frequencies unintentionally. So let's now summarize the design procedure for this Pierce oscillator. It's in fact very simple. It's really the same. Pretty much nothing has changed. All we have to do is replace the crystal with an L effective. We reflect all the losses at the output, and so our equivalent circuit looks like some L effective here. This is Vn, this is C2. Let's say this is the RO of the transistor. This is C1. I took the loss here and reflected it to the output. That gives me RL prime. Might have a bias resistor, say RB. This is the crystal losses. And so the total loop gain is GM of this transistor times RL, which is a parallel combination of all these resistors, times the feedback factor divided by N, which is C1 over C2. And RL is RL prime in parallel with RB, in parallel with RO, and so on and so forth. Same equations as before. For large signals, we use the large signal GM. We know in steady state the loop gain is 1, and that allows us to calculate the amplitude of oscillation based on the initial loop gain. Okay? Any questions about designing crystal oscillators? Of course.
No, I was just wondering, so if I intentionally want to oscillate on an overtone or on a higher order frequency, I can design my loop somehow that I get a loop gain lower than 1 at the fundamental and higher than.
That is definitely possible. And it's a little bit difficult with the Pierce. With the Pierce, you can play some tricks. You have to introduce an external tank to kind of artificially kill the loop gain at low frequency and allow it to get high at the frequency of interest. But you're going to end up loading the circuit a little bit. We'll look at another circuit that has less loading. Yeah, we'll get to it. All right, so one of the issues with crystal oscillators is simulation. It's not easy to simulate a crystal oscillator. And the reason for that is if we go back and look at our second order system, we found that we had poles on this circle with radius omega naught. It's j omega, this is sigma. And as we applied our loop gain, we end up with poles in the right half plane. And this distance, sigma 1, basically determines the growth rate of our initial disturbance. So some initial disturbance causes the envelope to grow, and this growth rate is related to sigma 1. So sigma 1, let's call it 1 over tau. Tau is q over omega naught 2 a loop minus 1. And so for a typical case, let's say I've designed my circuit to have a loop gain of 3. Well, that means that tau is q over omega naught. Immediately you see the problem. If q is equal to, let's say, 1 million, that implies you have to simulate 1 million cycles, 1 million RF cycles, just to see an amplitude growth by a factor of e. Let's say envelope growth by a factor of e, which is about 2.71. So that means that you're going to need several million, tens of millions of oscillations before you actually get to steady state. And so that's, you're going to upset a lot of people using the same computer if you simulate this thing more than once. So there's some options to get around this. So the cheap and dirty way is basically use a fake crystal with a Q of, let's say, 10 or 100 or whatever you like, but something reasonable. And you have to be careful. You have to keep Rx the same, but so you get the same loop gain, but you have to adjust the values of Cx and Lx so that the affected loading of Rx gives you the right Q value, which is now, let's say, 10. Okay. The better way is actually to use PSS or harmonic balance, because these options assume the circuit is in steady state, sinusoidal steady state, and so you won't be able to observe the amplitude growth, but at least you don't have to wait 1 million cycles or 10 million cycles to see it happen. Okay? All right. Let's talk a little bit about overtone. In fact, we'll get there by looking at another crystal resonator that uses the series resonance mode. And the idea is that let me build a classic diff pair oscillator. It's my tank. This is C1, C2. And I take this and I feed it back to the input, but I put a crystal in series with my feedback network. That means that at resonance, at series resonance, I just see Rx here and I see a voltage divider and the loop, so that determines the loop gain at resonance. If I move away from resonance, this thing either looks like a capacitor or an inductor, and it produces a voltage divider which actually kills the loop gain. So if you think about it, if I move away from resonance, if I didn't have this crystal, if I just shorted this, the frequency response would be determined by this tank. But because I've put this in the feedback loop, the frequency response of the feedback is now a function of this tank. So, so this tank here is low Q. Maybe it's between 3 and 20, and it's tuned only approximately to desired tone, which could be the fundamental, or an overtone. Okay? So the transistor Q2 at the frequency of oscillation, Q2 sees basically a resistance, because it's in resonance, R tank, which is this RT in parallel with N squared through this cap divider. The resistance of this guy, Rx, in series with RB prime, which is RB in parallel with, let's say, the diff pair input impedance. Okay? And N, as before, is just our capacitive transformer feedback factor, and Rx is the crystal loss. So the loop gain at resonance is the GM of the differential pair, small signal GM, this tank impedance RT prime divided by N multiplied by this additional factor, which is the resistive voltage divider at the base of Q1. And again, just as before, we designed this to have an initial loop gain somewhere between 3 and 5. Okay? But in general, as we move away from resonance, so this is at resonance, in general, the loop gain as a function of frequency, same GM, tank impedance, same feedback factor, times now a function that is very strongly dependent on the crystal. So if I look at this loop gain, let me call this term here AL1 and this term AL2. If I look at AL1, this is more or less what we've been looking at for the past few lectures. It's some low Q resonance transfer function, right? So it resonates, let's say, at omega naught. Okay. If I look, on the other hand, at AL2, it's basically at resonance, let's say at omega naught. This is just Rx, and you get basically some divider, let's say 1/2. As you move away from Rx, though, this turns into a large impedance, and this gets very small. And you don't have to move very far away for that to happen. So if you actually do a plot, you see that it's a very sharp resonance. And likewise, at 3 omega naught and 5 omega naught, you see a very sharp resonance. And so this is very frequency selective. Whereas this is not. This is only coarse. So the actual loop gain is a product, so this is AL1, this is AL2, is a product of these two. So the actual loop gain will look something like this. Let's say this is 1. The overtones now have a loop gain less than 1. This is somewhere between 3 and 5. And you can see that in this case we've selected our fundamental mode. And because the frequency, the feedback factor, the loop gain is so frequency selective, this will also have very good frequency stability. It will not oscillate at any frequency except the frequency that it likes to oscillate at. And so it has a good noise rejection. Now you can see how you might design an overtone mode oscillator. What you would do is you would take, again, that very selective response and now center your tank around, let's say, 3 omega naught. And so when you multiply this out, what you get is something that looks like this, where now this is 1 and this is something like 3 to 5. So now the loop gain is bigger than 1 only at one frequency. That's at the frequency that I desire, which is 3 omega naught, and I've suppressed the fundamental mode. Okay? Questions? Good. All right, so now another fundamental question comes to mind is, so you have these crystal oscillators, they're very nice, but their frequency doesn't go beyond, let's say, a couple hundred megahertz. So one option is you go use MEMS resonators, right? But MEMS is an add-on. It actually doesn't really exist today. In a year or maybe a couple years, you'll have the option of maybe using MEMS resonators with a standard process. But again, it's going to be much more expensive. So if you want a low-cost solution, you need some way to synthesize a higher frequency. So what we'd like to do is we'd like to somehow go from frequency on the order of 10 megahertz or so and somehow drive, let's say, the LO of our system. This gives us precision, right? We need to be able to, we need two things. We need a precise frequency reference, right? So when I tell you let's communicate at a frequency of 1.001 gigahertz, somehow you guys have to be able to synthesize 1.001 gigahertz. If you build an LC tank, there's no way you're going to hit that resolution. It's going to be moving all over the place. So you need a precision. You also need low phase noise, because even if you guys somehow or another, using an atomic clock, manage to get your LC tank just tuned to 1.001 gigahertz, and then you leave it alone, it's going to start moving around like crazy, right? It's not stable. So that means that basically we need it to be precise, we need it to be stable over temperature and process, let's say. We also need low phase noise. We talked about phase noise last lecture. The phase noise that you would get out of a low Q oscillator often is too high to use in especially narrowband circuits. We had the issue with spectral leakage. We also had the issue with reciprocal mixing. And we somehow need to generate this, so we need to generate a reference quickly. That's because for a whole host of reasons, you might want to change the frequency at which you're communicating at. You might want to change your channel, right? You're at 1.001 gigahertz, you might go to 1.002 gigahertz, and you want to do that quickly. That might be because you're using frequency hopped method of avoiding interference with other people, or it just might be you need to move to another channel because there's too much interference on a given channel. So we need a mechanism that lets us take this precise frequency and somehow control this oscillator. Yes?
Does the high impedance of MEMS resonators hurt their application for oscillators?
Not for oscillators, no. It hurts them when you try to use them as filters, but for oscillators it actually helps. Alright, so the way we do this, the most popular way to do this is to use a phase lock loop. The idea is that I'm going to take my crystal and use it as a reference. And I'm going to go through a circuit that's going to compare the phase of this circuit with the phase of a divided down version of my oscillator. And I'm going to filter this phase difference, and with it I'm going to control my oscillator. Okay, so this is a feedback loop. So this is a phase feedback loop. The reason I have to use a divider is that this might be at a gigahertz and this might be at, let's say, 10 megahertz, right? So this divide ratio is on the order of 100. But if I could somehow lock, basically generate a control voltage that varies precisely in step with the way this is changing in order to keep it constant, then this will be almost as clean as this reference, right? So the whole idea is, you know, when a free-running LC oscillator has no frequency stability. It has no way of knowing that it's veered off course. It's like a driver driving in the desert, and someone says drive straight, and you know, the only, you know, if basically if you're trying to drive straight, and you know, you're basically just tiny little variations in holding the steering wheel, a little rock hits your wheel, drive 1,000 miles, and then you see, wow, I didn't really go straight, did I? But now you put a line in the middle of the road, and you say, just stick to that line. So if in case you get off the road, you say, oh, there's the lane again, you get back on. That line is this frequency reference. It keeps you in step, and there's a feedback loop doing that. Okay. So this is a highly nonlinear feedback loop. We're going to linearize it in order to analyze it. You can also use tools like MATLAB or Verilog A to analyze these kinds of circuits. It's basically what we call a mixed signal circuit because it involves a high frequency oscillator. It involves dividers, which tend to be digital circuits. Phase detectors. You can also have frequency detectors or a phase frequency detector. Are also generally digital style of circuits, although you can build analog phase detectors. We'll talk about that a little bit. And then you have filters, which typically are either R's and C's or they're op-amp C's kinds of filters, which control our oscillator. So there's lots of components in this PLL loop, and some of them are digital, some of them are analog, and some of them are RF, and they all need to work together. So this is a big mixed signal design. Okay, so you guys already know how to design VCOs. So the VCO we're not going to talk about anymore. We'll focus on a couple of blocks. Focus on phase detectors because most of you probably don't know how the phase detectors work. So let's spend a little bit of time with the phase detection. So let's first of all observe that a multiplier can actually work as a phase detector. So the idea is that if I had an ideal multiplier and I come in with a signal A cosine omega t and B cosine omega t with some phase difference and multiply them together, I low pass filter and look at the output. Okay. So this is mathematically very simple. The output is just simply A times B cosine omega naught t, cosine omega naught t plus phi. And using a trigonometric identity, I know this is simply AB over 2 cosine of phi minus cosine. So it's the difference frequency and the sum frequency. So the difference frequency gives me phi. The sum frequency gives me cosine 2 omega t plus phi. And because I low-pass filter the output, I get rid of this high-frequency component, and I'm more or less left with AB over 2 cosine phi. Okay? So this is actually already, you can see, it's not a linear circuit. If I look at the V out transfer function versus phi, it looks like cosine. And you can see that if I want to maximize the gain of this circuit, I should operate, the gain is maximum right around here, right, where cosine is pi over 2. In other words, the slope, small signal slope of this circuit varies depending on where you operate it. Best point is right here, and that's pretty clear. We define KD, which is our linearized gain, which is the slope of this transfer characteristics. It's minus AB over 2 sine phi, the phase difference. So the best gain occurs for phi equals to pi over 2. And at that frequency, the gain is basically AB divided by 2. This is sometimes called a quadrature phase detector because it likes to operate in quadrature to give you good gain. Well, I'll say that this style of phase detection is really only used at really high frequencies. If you're locking to an optical source or you're building a really high frequency loop, you might use a multiplier. Because these two frequencies are actually quite low compared, low relative to today's technology, right? The reference frequencies are on the order of megahertz, tens of megahertz. So these circuits really can be purely digital. There's no reason to use complicated analog circuit here when you can build really cheap digital circuits, okay? And by cheap, we're talking really cheap. For instance, you can even use a simple XOR gate as a phase detector. So how does that work? Well, we just take the two inputs, A and B, and we low-pass filter them, and we'll see that this actually acts like a pretty good phase detector. Remember, the XOR circuit, if we look at its truth table, if the inputs, basically if either input is 1, you get an output of 1, but if both inputs are 1, you get 0, right? So if we look at, let's draw two waveforms. Let's say you have a square wave, 50% duty cycle coming in like this, and let's say you just have a phase shifted version. So let's say that this version is leading by just a bit, right? So if I now look at the output, so this is A, this is B, but when the inputs are both 1, I generate 0. Now only one input is 1, so this gives me VDD output. And then it goes back down to 0. Both inputs are 0, so it remains 0, and until again both are equal to 1, and then it goes back to 1 again. And so you can see here that this circuit is only 1 when 1. So because we low pass filter this, what we care about is the average value of the output. And you can see now very clearly that if these two circuits, if these two signals were perfectly in phase, then the XOR circuit would give us a 0 output, right? Because it's always either both are 1 or both are 0. So I'm either here or here. The worst condition, the highest output I could get, is if they're perfectly out of phase. So if they're perfectly out of phase, one signal is doing this, another signal is doing this. So the output would always be 1. So if I draw a transfer function V out over here versus the change in phase delta phi, then for 180 degrees phase shift, the output would rail at VDD. For 0 degrees phase shift, the output would be 0, and for any other difference, the output would lie on a line somewhere between 0 and VDD. So this simple circuit is actually a very simple, nice, cheap phase detector. Okay? Debo, you have a question?
So, what's the use of the low-pass filter?
Without the low-pass filter, you'd have all sorts of higher-order harmonics, right? You'd have to do so you think about the Fourier series of this. And since this is low frequency, you will see second harmonic, third harmonic. So you're suppressing all those harmonics. Remember, what you really want here is a constant voltage. Not constant voltage, but you want a voltage that tells you how far the phase shifts are off. So you can filter this, get rid of the high-frequency noise in this signal, and then apply this to the control line to pull the phase of your VCO to correspond exactly to the phase of your reference. Okay? Christian?
That circuit by itself can only tell you if the phase is positive, though, right? I mean, if the phase was negative, wouldn't it pull the signal in the wrong direction?
That's right, but it turns out that there's a problem with this in that the slope basically changes. As you go beyond pi, the slope then goes the other direction, and so the gain of the feedback loop changes. And in a real PLL, what you get is cycle slipping. What happens is that for a period of time, loop gain is positive, you go in the wrong direction, but it's a self-correcting mechanism. So even if you start out with the wrong direction, it will basically slip into the right phase. And so it's a very again, I should emphasize, a very nonlinear circuit until you get the phases very close. Once the phases are very close, it all acts like a small signal circuit, and the analysis that you do applies. Okay? Kevin?
Is there any advantage to using the mixer for phase comparator then?
Not really. The mixer also is less linear than this, than this kind of mix. The mixer is only useful if you want to go to high frequencies, essentially.
And we don't have high frequency. We don't use phases at high frequency, right?
In some applications, you do. But for the application that we're talking about, frequency synthesis, because our reference is at low frequency, you don't need to. Because remember, if you look here, there's a built-in nonlinearity in this phase detector, because this is sine of the phase difference. So sine is approximately phi, if phi is very small. Right? But from a large signal perspective, so this is from a small signal. But from a large signal perspective, there is this sine, and it does also change signs, right? Slope is sometimes positive, sometimes it's negative. Okay? I mean?
Doesn't the overlap also have nonlinearity because it's not a straight line? Here also you have a nonlinear line because the overlap with phase is not a linear function. It's a sinusoidal function. It's going on a circle.
It's actually pretty linear. The average value is very linear.
But that line you're saying is straight line?
It's a straight line, yeah. It's a very linear process, right? Because it's just it's basically the pulse. The average value corresponds precisely to the difference in pulse widths, not pulse widths. The difference in times that they're not aligned, right? It's a very linear process. The only nonlinearity, of course, in reality occurs when these pulses get very narrow. Then things get kind of ugly, so it's pretty hard to hit that zero precisely. But for the most part, it's a very straight line. Okay, so so that gives you a little bit of insight into the phase detector. Let's see how this circuit actually works. I forgot to tell you guys how we synthesize a frequency programmably. So the beauty of this circuit is that, first of all, given a reference, I now have a high gigahertz signal, to this reference is in megahertz, I have a gigahertz signal that's very stable. We'll show you guys, probably next lecture, that it also has very good phase noise. Turns out that within the bandwidth of this PLL, I can clean up the phase noise of this guy. And another benefit that you get is that because this divider is also a digital circuit, essentially, I can change the division factor, right? I can go from a division factor of 100 to 101. That means that I can control the output frequency. So basically this loop is locked when locks the output frequency divided by n to f-ref. That means that the output frequency is n times f-ref. And since it's relatively easy to change the divide by an integer, that means that I can also easily achieve, let's say, n plus 1 times f-ref. So I can control the output within a resolution of exactly f-ref. Right? By changing the division ratio by just 1, the output changes by f-ref. So now not only have I devised a scheme for creating a simple, stable frequency at gigahertz, I can also program its frequency with a resolution of f-ref. Okay? So let me give you an example. Let's say you want to build a GSM cell phone. And the channel spacing is 200 kilohertz. Okay? So that means that the cell phone needs to wake up, listen to a control channel, and then hop to a given channel. So this is channel 1, 2, ... And so let's say, let's use a numerical example. Just for simplicity, let's use a gigahertz. So I have 1,000 megahertz, and my channel spacing, delta f, is equal to 200 kilohertz, or 0.2 megahertz. So f naught over delta f is equal to basically 10,000 divided by 2, is that right? Or 5,000. Okay? So that means that I should choose a reference. If I have a crystal, let's say at 10 megahertz, what I'll do is I'll divide it down by 5,000 to create a 200 kilohertz signal, and then I'll go into my PLL basically to generate a 1 gigahertz signal locked to a reference. Now if I want to change the channel from channel 1 to channel 2, all I have to do is divide this division factor by from 5,000 to 5,001, and then the output will jump to the next channel. Okay? So this is a very convenient way of synthesizing a frequency, and we'll continue with this discussion next lecture.